Have you ever looked at a butterfly's wings or a snowflake and marveled at its perfection? That's symmetry. But what if I told you that same simple idea is the single most powerful concept in all of physics, guiding us toward a final theory of everything? For a physicist, symmetry isn't just about looking pretty. It's about a deep, unbreakable rule. The laws of the universe don't change, no matter how you look at them. Rotate an experiment, fast forward it 1 billion years, or move it to another galaxy. Rules of the game stay the same. This elegant idea is our compass in the search for a single equation that describes all of reality. The revolution started with a brilliant mathematician named Emmy Noether. In 1915, she proved something that rocked the world of physics. She discovered that every symmetry in nature is directly tied to a law of conservation. Is physics the same today as it was yesterday? That symmetry requires that energy must be conserved. Is physics the same here as it is on the other side of the universe? That symmetry demands that momentum must be conserved. Suddenly, the most fundamental rules of our universe were just random day, were required by the very geometry of space and time. Einstein took this idea and ran with it. His theory of general relativity is a masterpiece of symmetry. It's built on the principle that the laws of physics must be identical for everyone, no matter how they're moving. This forced him to realize that space and time are not separate things, but a single, interwoven fabric. Space-time and gravity. It's not some mysterious force pulling us down. It's simply the curvature of that fabric. Einstein's unwavering faith in symmetry allowed him to predict black holes and bending of starlight long before we ever saw them. Now, let's zoom in. In the bizarre world of quantum mechanics, symmetry gets even stranger. Here, we find something called gauge symmetry. Imagine trying to keep a system perfectly balanced while changing parts of it independently all over the place. To maintain that balance, to preserve the symmetry, the universe actually has to create forces. The forces that govern our world: electromagnetism, the strong force holding atoms together, and the weak force causing radioactive decay, aren't just there by accident. They exist because the universe demands symmetry. Particles like photons and gluons aren't just found. The math insists they must exist to keep the cosmic books balanced. But, hold on, if the universe started out perfectly symmetrical, why is it so messy? Why do some particles have mass and others don't? Why aren't we just a perfect, uniform soup of energy? The answer is as beautiful as it is profound. The symmetry had to break. Think of a pencil balanced perfectly on its tip. It's symmetrical, but it's unstable. It has to fall. When it does, it picks a direction, and the symmetry is broken. In the early universe, the Higgs field acted like the floor. By falling into a stable state, it broke the initial perfect symmetry, and, in doing so, gave mass to particles. We exist in the beautiful ruins of a broken symmetry. Without that imperfection, there would be no stars, no planets, and no us. So where does that leave us? The standard model of physics, our current best explanation of reality, is incredibly successful. But it's incomplete. It doesn't include gravity, and it can't explain mysterious things like dark matter. This is where the next great idea, super-symmetry, comes in. It proposes a deeper, hidden harmony. For every particle of matter we know, like an electron, there's a secret superpartner that carries force, and for every force particle, there's a matter partner. If true, supersymmetry could be the bridge that finally connects the quantum world with Einstein's gravity, explaining dark matter and unifying the forces of nature once and for all. Ultimately, the quest for a theory of everything is a quest for unity. We started out seeing a world of separate things: fire, light, motion, but through the lens of symmetry, we've learned they are all just different faces of the same underlying reality. The final theory will likely be the discovery of apparent symmetry, a single, perfect mathematical state. In the first moment of the Big Bang, broke apart to create the magnificent, complex universe we see today. The story of the cosmos isn't written in words. It's written in the elegant language of symmetry. Thanks for watching. If you enjoyed this journey into the heart of physics, be sure to like and subscribe for more.